Alright, so in this lesson we're going to look at 3 sample problems dealing with conservation of energy. And the first one looks very similar to your problem that we dealt with the skier. We have a 15 kilogram block and it's going to slide down a frictionless ramp at a 20-degree angle, and the block starts at rest and slides 10 meters down the ramp. So if we use conservation of energy, initial total energy is equal to final total energy. There are no friction, no non-conservative forces. The only force acting on the block is gravity and, well, normal force, which does no work. So mgh initial plus 1/2 mv initial squared for the block is equal to mgh final plus 1/2 mv final squared. Now, a lot of times when we deal with conservation of energy, some of these terms cancel out. We know the initial velocity is 0, so 1/2 mv initial squared becomes 0. And we know h final we can define as 0, bottom of the ramp, so mgh final is also 0. Excuse me. So let's kind of work this problem out. So we have mgh initial is equal to 1/2 mv final squared. The m's cancel out. The mass of the block doesn't really matter. So I got gh initial is equal to 1/2 v final squared. So h initial is this height here, which I can find by saying x sine of 20, excuse me, I kind of confused myself. Got a right triangle here. X sine of 20 is h initial. So g times h initial is equal to 1/2 v final squared. Multiply both sides by 2. Square root both sides. Plug in the numbers 9.8, 10, 2, and sine of 20, and you get 8.19 meters per second is the speed the block moves at the bottom of the ramp. So this technique is actually a little bit easier than trying to use work energy theorem, but we're ultimately using the same ideas or the same principles. Second problem that I have a daredevil. He's going to jump a canyon as pictured above, and it says what speed, the speed at which the daredevil approaches the canyon is 38 meters. It looks like the initial height of the canyon is 75 and the final height is 35, and it wants to know at what speed does the daredevil land. So we know initial height 70, initial velocity 38, final height 35, find final velocity. We can actually make use of total energy initial equals total energy final. So kinetic energy plus potential energy initial equals kinetic energy plus potential energy final. There's what kinetic energy and potential energy looks like. 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. All of the m's cancel out. The mass of the biker doesn't really matter. So I get this equation. 1/2 v initial squared plus gh initial equals 1/2 v final squared plus gh final. So now I'm going to solve for v final. Looks like subtract gh final to both sides. Do a little bit of algebra. I'm going to make it g h initial minus h final. Multiply everything by 2. So I get v initial squared plus 2g h initial minus h final equals v final squared. It's worth pointing out at this particular point that we have v initial squared plus 2ax equals v final squared, what we already saw way back in the toolbox equations. Square root both sides. Plug in my numbers to calculate v final, and I get 46.2 meters per second is v final. So here we go. We have a problem where we need to keep all 4 terms, but still mass cancels out. The third problem that I have is the Atwood's machine problem. And the way we do this problem, we want to find the velocity when the mass, when both masses, when m2 strikes the ground, is I would calculate the acceleration of the system, and then from the acceleration of the system, I would calculate velocity by doing kinematics. So a few things that we can say if we're going to treat this like a system is that the initial potential energy or initial energy of the system is equal to potential energy of block 1 plus potential energy of block 2 plus kinetic energy of block 1 plus kinetic energy of block 2. So there's my total energy of my system initially. Potential energy block 1, potential energy block 2, kinetic energy 1, kinetic energy 2. Same thing for final energy. Potential energy 1 final, 2 final, kinetic energy 1 final, 2 final. So there's a few things that we can say are true that can cancel out. First thing that I can cancel out are the things that are going to be equal to 0. The system starts at rest. Kinetic energy of both 1 and 2 initially is 0. And if block 2 hits the ground, the potential energy of block 2 final is 0. There is one other term that I can cancel out, and that's the potential energy of block 1, initial and final. The reason for that is the block stays on or cart 1 stays on the table. It's at 105 centimeters initially, it's 105 centimeters final. Those two numbers are the same. So I can actually cancel them out because they're going to be the same on either side. So I'm left with, out of the big mess of equations that I had before, is something pretty easy to work out. Potential energy 2 initial is equal to kinetic energy 1 final plus kinetic energy 2 final. So if we plug that in, the one thing I know is that the velocity of both these objects are going to be the same. They're connected by a string. Multiply both sides by 2. I can't cancel mass off because the masses are different. So 2m2ghi2 is equal to m2 plus m1 v squared. Divide by the sum of the masses and square root. And when you plug in that number, you get 1.67 meters per second when you plug in all the variables, all the values. The one thing I'd probably watch out for is to make my height in meters, not in centimeters, or else you get some tricky things happening. So those are 3 problems that deal with conservation of energy. One, a system type problem. One, a problem where you have variables both before and after. The other one, a problem where you can cancel some things out. It's a basic, straightforward one. We'll look at in the next lesson is what do we do